Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is variable resistors. Our objective is to take a close look at a three-terminal variable resistor known as a potentiometer. Even with a dizzying array of standard-sized resistors available, you're sometimes left scrambling for a particular size. As an exercise to the viewer, I invite you to go ransack your school supply room for a 140 ohm resistor. Go ahead, tell them I told you it was okay to do so. You'll quickly realize that a 140 ohm resistor isn't commonly available inside the standard size set, and you'd have to resort to some level of trickery to accomplish the desired task. Given that resistors are manufactured with a specified tolerance, you might be able to paw through a roll of plus or minus 10% tolerance 130 or 150 ohm resistors, the next lowest and the next highest standard resistors available, and find an unusually high 130 ohm or an unusually low 150 ohm that exactly satisfies the 140 ohm requirement. Additionally, one could in effect create a 140 ohm resistor using various combinations of series and or parallel configurations. For example, we could place a 120 ohm resistor in series with a 20 ohm resistor for a total resistance of 140 ohms. Or we could place two 270 ohm resistors in parallel in series with two 10 ohm resistors in parallel. The two 270 ohm resistors in parallel have an effective resistance of 135 ohms, and the two 10 ohm resistors in parallel have a resistance of 5 ohms. Taken in series, 135 ohms plus 5 ohms yields the desired total resistance of 140 ohms. It should be evident that numerous other combinations of standard-sized resistors could also yield 140 ohms of resistance. For example, you could take 7 20 ohms in series, or if you had the patience, 141 ohm resistors in series, all with an increasing level of annoyance and busy work. It would be far more desirable to use a single variable resistor in which you could dial it into the exact value you require. This device is known as a potentiometer, sometimes known as a rheostat depending upon application. Informally, they're known as pots, trimmers, or a combination of both, trim pots. A potentiometer is a three-terminal device. The two outside terminals, A and C, represent the beginning and end of a fixed conductive path with a constant resistance. The A2C resistance is the nameplate value of the potentiometer. Regardless of the status or position of the B terminal, the A2C resistance remains a fixed constant value. For example, a 1 kilo ohm potentiometer always has 1 kilo ohm of resistance from terminals A to C. The schematic symbol for potentiometer reveals the purpose of the middle lead B. It is a midway station on our journey from A to C. What's super handy about this midway station is that the physical position of terminal B is adjustable via a screw, a wheel, a slider, or a knob. This movable B contact is sometimes called the wiper arm because it moves up and down the resistance path from A to C. In effect, by varying the position of the B terminal, we are varying the length of a conductive path. If you recall, length is one of the three main properties that influence resistance, in addition to resistivity and cross-sectional area. If the length of a conductive path is increased, the resistance is increased. Conversely, if the length of a conductive path is decreased, the resistance is decreased. Given a potentiometer has a constant resistance from terminals A to C, every time I increase the length of the path from A to B by adjusting the position of the wiper arm, I am decreasing the length of the path from B to C. Can you see where this is leading? The resistance from terminal A to terminal B, RAB, plus the resistance from terminal B to terminal C, RBC, equals the resistance from terminal A to terminal C, RAC. If it helps you understand the three-terminal potentiometers, you can visualize the internal structure as a pair of series resistors, RAB and RBC, where the total resistance from A to C is the full nameplate value of the potentiometer. If you increase RAB by 1 ohm, you decrease RBC by 1 ohm and vice versa. Consider a 1 kilo ohm potentiometer with a constant resistance of 1 kilo ohm between terminals A and C. Assuming position of the B terminal is a linear proportional resistance, and the B terminal position at 50%, it means half of 1 kilo ohms, or 500 ohms, appears between the terminal A and B, and the remaining 500 ohms appears between terminals B and C. If, however, the B terminal wiper arm is repositioned such that 60% of 1 kilo ohm is apportioned to AB, and 40% of 1 kilo ohm is apportioned to BC, the resistance from AB is 600 ohms, and the resistance from B to C is 400 ohms. Get it? For every ohm of increased resistance between terminal A and B, there is a corresponding ohm of decreased resistance between B and C, such that total resistance between A and C remains constant at 1 kiloohm. Let's put your understanding of this simple concept to the test with the following scenarios. Given a 2 kiloohm potentiometer with 200 ohms of resistance known to be between terminals A and B, determine the resistance from B to C. Given a 1 kiloohm potentiometer with 780 ohms of resistance known to be between terminals B and C, determine the resistance from A to B. Finally, given a potentiometer with 200 ohms of resistance from A to B and 300 ohms of resistance from B to C, determine the nameplate value of the potentiometer. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. If 2 kiloohms appears from A to C and 200 ohms of resistance is known to be between terminals A and B, this suggests the remaining 1.8 kiloohms appears between the terminals B and C. If 1 kiloohm appears from A to C and 780 ohms of resistance is known to be between terminals B and C, this suggests the remaining 220 ohms appears between terminals A and B. Finally, if 200 ohms appears from A to B and 300 ohms appears from B to C, the nameplate value of this potentiometer is most likely 200 plus 300 or 500 ohms. Now that we've got a good idea how the position of the B terminal affects how total resistance is apportioned between the terminals of a potentiometer, let's take a look at how potentiometers are employed in circuits. Consider the following circuit incorporating a 1 kiloohm potentiometer hooked terminal A to C, where the B terminal is positioned exactly in the center. Half of 1 kiloohm appears between A to B, and the remaining half of 1 kiloohm appears from B to C. What is the resistance seen by the source? If you said anything other than 1 kiloohm, please take the time to viciously slap a wooden ruler across your knuckles. Series resistances add up. The source sees the full resistance of RAB plus RBC, which equals the full nameplate value, in this case 1 kiloohm. Although the B terminal is exactly in the center, the B terminal isn't being employed. This is to suggest that no matter how one tweaked, twiddled, dorked, diddled, turned, spun, pulled, or pushed the adjustment screw, or even if you screwed it so hard it fell off in your hand, a potentiometer configured in this fashion would always present a fixed resistance equal to its nameplate value. We'll examine this particular configuration in later lectures on series circuits discussing voltage division. For now, simply realize the customizable nature of the potentiometer resistance isn't being fully realized when wired in this fashion. In order to make a truly variable resistor, one must make use of the central B terminal such that resistance is now a variable customizable quantity. Here's one such circuit that allows this ability. Given the B terminal is adjusted to a 50% position, current travels through only half of the 1 kiloohm potentiometer and the source sees 500 ohms of resistance. If the B terminal is adjusted such that 75% of 1 kiloohm appears between B to C, current travels through 3/4 of the 1 kiloohm potentiometer and the source sees 750 ohms of resistance. Similarly, if the B terminal is adjusted such that 40% of 1 kiloohm appears between B to C, current travels through only 40% of the 1 kiloohm potentiometer and the source sees 400 ohms of resistance. Deployed in this fashion, we've in effect created a 2-terminal variable resistor. Sometimes you'll see an ordinary 2-terminal resistor schematic symbol that includes a slanting arrow indicating this is a variable resistor. Additionally, you might see a potentiometer wired in this fashion to create a variable resistor. Note terminals A and B are tied together with a 0 ohm wire. It helps to understand this configuration if we again visualize the potentiometer as 2 series resistors, RAB and RBC. If terminal A and B are tied together with a 0 ohm wire, we've effectively shorted out RAB. Any current will be routed around RAB, however it must still travel through RBC, such that the potentiometer effectively yields a resistance equal to only RBC. Regardless of the schematic employed, stop to consider the consequences of sliding the B terminal from one extreme to the next. Let's say the B terminal is adjusted such that 100% of 1 kiloohm appears between B to C. At this upper extreme, the source would see 100% of 1 kiloohm and current might be regulated to a manageable small value. However, if the B terminal is adjusted all the way down such that 0% of 1 kiloohm appears between B to C, at this lower extreme, the source sees no resistance and current might swell to an uncontrollable, dangerous level. The point is, pay attention and don't drop resistance too low, otherwise you might damage your circuit, your equipment, or yourself. Take your time and think about it. Really think about it. Take your time and think before you act. Don't just randomly push buttons, pull wires, turn screws, and hope it works out okay.